guys. Welcome to the fourth lecture. So today we're going to cover transfer learning, the GPT papers. There were three important papers that came out of OpenAI. A little bit about prompt engineering, and then supervised fine-tuning. So we're carrying right on here. So if you recall, actually it was last lecture, I talked about these kind of example natural language processing tasks. So there was a pre-2018 or so, there was a lot of, the natural language processing community had kind of split along some different tasks that were kind of a focus. So one of them, of course, was classification. And I showed this example last time where we're trying to kind of do like some kind of sentiment analysis, classifying different documents into different classes. Then there's this RTE recognizing textual entailment. There's this kind of logic problem that the community set up, and that had to do with kind of what follows what. Does something follow from something? You know, is there a premise conclusion relationship, a valid premise conclusion relationship between the sentences? So yeah, John spit off in his powerboat entails that John left. He left the scene. Then text similarity was very important. And we'll talk about this in the latter part of the course when we talk about like vector databases. The idea here is that, we have this idea that certain sentences are more or less similar to one another. Okay, so there was a gold standard that was collected from human beings. And so what was happening is that people were developing specific architecture, specific systems to handle this similarity problem. And then there was like question answering, and then the simple version of question answering is like multiple choice. So the question, and then you have, here are the potential answers, which one is it? Okay, so each of these, so lots of different work was going on in each of these areas where people were building specialized architecture. So lots of earlier work trained over task-specific corpuses. And they used lots of different kind of architecture. So specific architectures were specialized to the particular task. So they could be somewhat complicated, but they were specialized to the task. And the name of the game then was to play this kind of supervised learning game where, you have the training set, you have the test set, you have a validation set maybe. And then you go about over whatever your particular architecture is, you go about training that, and then you're aiming for a better score. And so there was like leaderboards on all those tasks developed, and you had different research groups trying to do well on the leaderboards. Okay, so that was kind of how it was set up. So what was the idea then that came along then next? And then by the way, these corpora are. I mean, there was communities built around getting these corpora, but it was like a lot of effort in terms of getting these supervised labeled test and training sets. Okay. Now the results themselves were always brittle. It was always kind of very, very specific to one particular task. So that's just kind of like was the nature of the beast back then, that we were just kind of getting a rather narrow, doing rather narrow on specific, kind of specific tasks. So when you took whatever you did over one particular task didn't really apply to other tasks. It was just a very narrow and brittle result over that task. And then if you change, for instance, like the type of inputs that are going in, then it would very quickly fall off. So for instance, if you're doing like, let's say you were doing classification over just like the public data, and then you took in a private kind of medical data, it might actually fall apart on that medical data because it's not very robust. Okay, so what was the idea then behind GPT-1? So this is like the very first GPT paper. So, transformers had just come out, and they figured, well, all we really need is a decoder sided transformer network. So, okay, so now we have GPT. And the very first GPT paper then was, what the idea behind this was the following. The aim was what's called transfer learning. So the idea was basically, hey, if we take all this text, like this web text or these book texts or whatever, and we train on that, we train a GPT that can do next token prediction, statistically representing the patterns that are in that kind of pre-trained data, is doing unsupervised learning over that pre-trained data. So if we take that and then we add a little bit more to it, just a little couple, just one little more architectural element or two, it depends. We'll add a little more architectural element to it. And then what we'll do is then we will play the game of task-specific evaluation. Maybe we'll go to like recognizing textual entailment, and then we'll put in a bunch of, okay, so then the question is, well, how do we do that? Right, so there's a leap here, the kind of interesting kind of technique that was used to kind of do this. But the general idea, though, is that can we do the pre-training, and then can that then boost our results when we do like apply, kind of a normal training to one of these tasks? Okay, so the question, of course, is, how does GPT do this and stay architecturally general? So how are they going to have like the pre-trained network, and then they're going to adapt that thing so that it can answer questions over in the specific task area? And this, I don't think it was them that come up with. I think I should actually find out what the paper was that originally introduced this, but I think it's a really, really a powerful idea. It's the idea of task-specific input transformation. So let's look and see how this works. So if we talk about classification, so classification, remember, is like, okay, does it go into, here's the text. Am I going to classify it as wholesome or dirty or whatever? I might have 10 different classes that I'll classify it as, or like what we'll later see is like, okay. So anyways, here's the idea. What you do is you take the text, whatever that might be. So the text in this case might be, for instance, let's go back here and see this text. We ate milk and cookies while we watched the sunset. Okay, that's a wholesome that's a wholesome text. So you put that start. You have a special start symbol. You put in that that text about the milk and cookies and the sunset, and then you have an extract symbol. So these are special symbols that you're putting in, and then you push that through a transformer. So the transformer here is GPT. Okay, you push that through a GPT. And then what's coming out of the GPT then, whatever the output coming off of the extract token, whatever that thing is at the very end of the head, essentially, whatever that is, whatever it's going to be D model length, whatever that is, you then put that into a linear layer with a number of classes that you have. So you're going to take that and you're building this extra little thing that's going to do classification over that. And then, as we'll see in a second, you're going to do learning over that, and they're going to do the learning just like the other systems we're doing, where they had the training set, the validation set, etc. They do all the learning then, and then they get the test set, and they can test it and evaluate how accurate it is. And the question is, are they going to get a significant boost in accuracy because they did all the pre-training? The answer, of course, is going to be yes. I mean, this is why. This is I hate to kind of play a spoiler there, but they're going to get it's going to have an impressive result. So okay, so that's easy for classification. What about entailment? Well, you put in start, you put in the premise, and you put in a special delimiter, and then you put in the conclusion. This is the hypothesis. Yeah, well, what the premise and the conclusion. This is the premise. This is the conclusion or hypothesis, and then you put that through a linear layer at the very end, right? So in the very beginning, of course, when you put it through a linear layer, in the beginning of your training, it's not guessing anything right. But what we'll see later is that you calculate a loss based on that, and then you push that loss all the way back through the full network and the linear layer. Okay, so that's kind of how it's going to be done. Similarity, you just have to do one thing that kind of gets the symmetry of it. You have to put, if I see, is this text similar to this text? Well, I have to do both directions. Okay, well, text 1 and text 2. Okay, then I'll push that through, but then I have to do like text 2 and text 1. I push that through, I add them together, and then I have again a linear model after that, a linear layer after that will then decide, well, what's the that will then say will generate a number that will be I guess you do a mean squared error on that, which basically indicates the level of similarity. Multiple choice is also similar. What you do is you just simply you put in the content and the answer. You put up all those through the transformer, and then you get out what's the output at the end of that. And then basically, like during its training, it will then find the one that should be the correct answer, and then push back the loss so that it goes to it rewards that one, or it affects that one. So this is the kind of the way it was set up. I mean, there's a lot of technical details that would be involved in actually implementing this, but well, the result showed strong transfer learning. Okay, so it actually showed that yes, that they were doing better. So let's see here. Here's some results coming out of GPT-1. And this is like, right. I mean, this is like, okay, these are from, they had, the types of classes they had here were, these are the ones. But if you notice here, they have number of pre-training updates. So how many times do we do pre-training, and then look at the results are kind of going up and to the right. And then right here, the deeper you'll do better, the deeper the transformer network is. Okay, so that was good. That was good to see. So yeah, strong transfer results. So that was good. Oops, let me go this other way. So right here, what I wanted to show, just to kind of, it's good to have here just for study. So let's just kind of look at the formalism of this. We have the tokens. So let's say that we have, I mean, we did this with byte pair encoding, but let's say we say, okay, we're going to hold the number of tokens at like 5,000 different unique tokens. Okay. Then we have a corpus, and that corpus is going to be an encoding of some body of text. So N here is very large. It's very, very large, and it's just going to wind up having like the encodings for all the tokens going through the text. Okay, and then what we have here is we have tau, which is just a mapping from the set of tokens to one and only to one to one and onto integers. So these are the identifiers. So the token cat might be 2000 or something, 2044. That's what its index position is. This is just like a little bit of thing I just developed here just to kind of get it so that we could then, when we talk about the hot encoding, what that is basically, it's a one hot vector. And this is just set up so we can get the matrix multiplication to work when we show the example here of here, let's just hopefully this will make sense to you guys. The weight, the W sub E, this is the embedding matrix. So the size of this is going to be, of course, the M is the number of tokens here, right? M there, tokens. See, there's the number of tokens. So it's going to be M cross the D model. So the D model is like 256 or something. I remember with it's usually some power of 2 or something. Something that it's certainly going to be something that's even because it's going to divide to get the heads. Right, so that's the token embedding matrix. Then we also are going to learn this W sub P, which is the weight, the positional encoding matrix. And then right here, when I say for a given Z, where Z is greater than, so this N here is the N here. What is N N is like the size of the corpus. That could be like 1 billion. So we're going to pick a Z, and K is the size of the context window. So it's got to be at least kind of positioned off greater than the size of the context window, because it has to position itself into the actual corpus. Because what we're going to do right here is we're going to pluck from the corpus, and all these transposes and all this other stuff, for those who are linear algebra minded, these are all correct. So the idea behind all this was just to kind of get a nice kind of single formalism that would show, rather than like pointing to the code. So sometimes code is truth and all that, but sometimes formalism is actually kind of better. So anyways, anybody who's interested, they can kind of like dig into that and see that this works actually. These are the transformer blocks. So however many levels we have, we just kind of run it through the transformer blocks. The transformer blocks, of course, then that's the whole the query, key, and value matrices, and that the kind of the way you combine those together, etc. So the formalism is not covering that, but that we did cover in some detail earlier. This is the output. These are the logics coming out of that, which the logics then go back in to get the actual symbols coming out. We can get the, we also do that, whatever's coming off the output, we do that through the embedding matrix, okay? Because it's going to have to kind of go back onto the embedded matrix. And then what we do is then basically what we're doing is we're trying to see, okay, this position Z in the corpus, if I take everything before Z, right? These are all the symbols before Z up until Z minus 1. Then what I need to do is I need to basically calculate the probability via a softmax of the logics coming out of this thing. And then that is softmax then relative to C sub Z here, which is that token we're trying to predict. So the mapping there is just giving us this number here, which one we're going to be looking at here. Okay, because it's going to be that at that one position, we want to see what the softmax is. That's what the probability is of this thing here. Now the loss, okay, so that gives you a kind of formalism of GPT. Now the loss, then what this is doing a full epoch in this formalism here, doing a full epoch over the corpus. And what we're trying to do is we're calculating a loss over that full epoch. And then what we're trying to do is we're trying to minimize that loss, right? So that's the that's why we have the negative out front, right? Because of the logs. So so anybody who's interested, really kind of like trying to get it to really understand it in a really deep level, I would point you toward this here and then digging through this formalism. Okay, right. So right, and then once we have that, once this right here was just GPT. Then what we have is this supervised fine tuning for transfer learning, where we have the class labels, and of course this is going back into this right here, the class labels of this. Anyways, it's the class labels coming from the training set. Right. Okay. So those are the class labels Y. Then we have the label data set. So this is where we actually have the supervised data set coming from maybe some corpus in the literature or something, where this is the label Y. So that could be like for classification or something. Then of course we put it through. We calculate the probability like we did in the last slide there. But then what we do is now we have another matrix, which is this weight matrix. Which is kind of over the last thing coming out of the model, so that it can kind of then calculate a loss right here. So this is the loss based on what it should be guessing Y sub I here. So this will wind up being the loss, the L sub 2, and then what we do is we combine these together. So we combine the L sub 1 of this of the underlying GPT and the L sub 2 of learning the task specific problem. Okay, and that turns into the full loss, and that's the full loss during our training is what we use to change the weights. So an important thing to remember here, though, of course, is that the initial weights were all like they went through a giant training session to get the initial weights, right? The initial weights, we weren't even looking at this when we did the pre-training. Now we're talking about doing the training. We're talking about the supervised fine tuning for the particular class. So we do that after, but that still can affect the underlying weights of the earlier model. And this lambda here will kind of regulate to what extent that loss will be accounted for in L sub 3, which is the loss of the supervised fine tuning for the transfer for learning. So what we're doing here is and we'll see this a bit more when we get to pure SFT. This is for transfer learning still. But what we're doing here is we're taking this corpus when we're doing the training on this. We're taking like a whole bunch of background text. We're getting an earlier model based on that's kind of has some intuition about how language works, and then we're cramming down on top of that changes to its weights and the weights of that last layer that does the class labels. We're cramming down the training set into that. So that's just important to see that's actually what's going on. And then we do much better on the, they got state-of-the-art results on a lot of problems. So when these problems that they were applying this to, they were getting state-of-the-art results. So that was kind of like, wow, okay, that was pretty impressive. All right. So then what happens is then we have GPT, the second paper come along. So this is 1 year later. This is language models are unsupervised task learners, multitask learners. Okay, so what does this mean? Okay, so what they basically said is this. They said, okay, well, this last layer where we're doing like the class variables, maybe let's forget that for now. Let's just run this over a giganto data set, and then just present the task-based transformations as zero shots. Okay, so what does that mean as a zero shot? Well, what it means is the following. It means that we're basically just going to take the problem and we're going to say, all right, fine, here's the problem. We're just going to shove this problem in, and then we're going to look and see what is the next token predicted or next sequence of tokens predicted. We're just going to kind of push that in there and make that happen. So So what would be there might be some a little bit other tricks to do to kind of play around with that, but it kind of might be like this. Like just think of it this way: if I went and I trained on a whole bunch of background data, and then I said, and the capital of Austin, I'm sorry, and the capital of the state of Texas is, okay, now there's all the different tokens or, token sequences or whatever in the language that could come from. And the capital of the state of Texas is, now, if we went and we see New York, that has it's got like just like puny little amount of probability in the pre-training for New York. But we walk through what are the actual answers, and we look and we say Austin, which is the capital of Texas. Now, if we just basically look and see, well, what's the most likely next word predicted, and we're just going to go to that one and say, okay, that must be the answer. That's giving it just a simple one shot or a simple zero shot. Just putting the thing in and looking at the problem. Now, it might be that when you give this to like the GPT that's been pre-trained, the probability of Austin actually is kind of low. It's like 20%, but it's much higher than anything else. Okay, so you take that max and you say, well, okay, I can pull off by looking at the distribution. I can pull off answers out of that sucker. Okay, right? So that is the idea of just kind of running things as kind of zero shots. Just like, all right, let's just kind of look and see what the distribution is coming out of the thing. So we don't have to do this kind of like fancy stuff. And let's just see. We have this hunch maybe that that if we train this over a lot of data, that we'll see it get better and better with the more data we train it on. And so the gigantic data that they trained on was web text. And the number of parameters in their model was 1.5 billion parameters. So that's I don't know, how big did Giga Turtle get in our recitation? I don't know. This is a lot bigger than Giga Turtle. And it performed reasonably well. So they did actually see that, okay, that actually kind of worked in a way. That kind of worked. But as we know, 1.5, that's chicken feeds in terms of the size of that kind of model. So now comes GPT-3. This is the scale up. They say, no, okay, look, they got clearance to run this thing over. So so GPT-2 and GPT-3 are very similar. They're getting rid of the task-based encodings and all that, and they're just trying to kind of grind the problems by directly looking at like the next token probabilities coming off of the GPT. Okay, so they're not doing any task-specific training at all. Okay, so now they got they got lots of resources. I mean, this is in 2020. I mean, $4.6 million. I mean, that's they got some money to do this. And it was the size of the model was 175 billion parameter model. That's what they were learning off of. And it was the web crawl. It was the web crawl data that they were running over. So it was a lot of data. And it exhibited what's called in-context learning. So let's just talk about what that means. It's kind of an important kind of concept here. So the way they envisioned it is they say that learning has two loops. The outer loop of learning is basically the stuff we've been doing in terms of just like pushing back loss, doing the gradients. So stochastic gradient descent, okay, building up the model. The second part is what they call in-context learning, which I'm not sure if I want to call it, would want to call it learning, but the idea is this. The idea is that if you pack a whole bunch of examples, so like right here we have like a bunch of examples of arithmetic. We're basically saying, okay, so we're building up a much larger prompt now. We're not just kind of giving the zero shot of the question, right? We can still do that, but we're not going to do that. What we're going to do is we're going to give it a whole bunch of correct examples, and we're going to pack that into the context window. Okay, up to the point where last thing we can do is squeeze in the question. And what is 6 plus 11? And then we want to see what the next token is that's going to be predicted. All right, I hope it's 17. Right. So that's the idea. So the in-context learning is the idea that, well, you get this kind of right in the middle of the context, you can do learning by putting in examples. All right. And they have an example here of like spell correction and English to French. Okay. So this is pretty, this is where everybody really kind of got excited here, because what happened here is that, look at this. We have the green line here. And this is what that, like a small model. Right, 1.5 I'm sorry, 1.3 billion parameters. And these are the number of examples that are fit into the context window. So it doesn't get up, it gets up to 10 or, maybe like, I don't know. This right here is 10. So it's not that many, right? Because the context windows have a limited size. But look what the most important part of this, and this is what got everybody so excited, was that, this is over these kind of over, a particular corpus. Look what happens when you actually scale the model up to a larger size. I mean, this is more compute to do all the pre-training, but it does better. It does a lot better. And then when you get up to one point, like the big one for the GPT-3, which was, by the way, the basis of ChatGPT, the very first ChatGPT was built upon GPT-3. So the 175 billion. Right. So look what you get here is here's one shot where you're just giving one problem, but look at how well it does, how much better a bigger model is doing. And so then it's kind of like like everybody was off to the races, because then it says, well, the name of the game now is let's just get more and more data to train on. And I mean, this is like one of like the first scaling law, right? Let's get more data to train on, and let's have a bigger model to capture it, and we'll get improved performance. And if this continues on, then we'll reach AGI or something. So I think some people were saying we would reach AGI by now. So, and they did this over just a whole bunch of different corpuses, corpora. So, and it was everything was showing the same kind of trend. Okay, that it really does get the bigger models do better, a lot better. Look at these are doing so poorly until whomp, it just kind of scales up. Really, just kind of becomes really, yeah. So this is kind of showing a bit of the magic. So this is yeah. So this was they were off to the races. Okay, so now what I would like to do is talk a little bit about, so again, this was over web data, so all the stuff on the web, right? And so this Shoggoth meme, okay, yeah, so I mean, I encourage people to watch this Shoggoth video. I think it's pretty cool. So the Shoggoth is from, so the Shoggoth meme is basically comparing LLMs with the Shoggoth, or the Shoggoth, I think it's Shoggoth, which is a monster from H.P. Lovecraft. So this alien race had basically crafted this thing as a shapeshifter, and kind of, it almost like it did pre-training on the thing. But then they kind of lost control of it. So it was supposed to be a servant, and then it kind of like, it's like a kind of classic thing of it kind of breaking control. But the idea behind the Shoggoth myth is basically this, is that this Shoggoth is like the whole kind of fusing of all this web data together. But then what we need to do is we need to align it. We need to make sure that there's a lot of junk out there. We don't want our LLM to be speaking. So we need to, and also all we have in the beginning is we just have the raw next word prediction. What we would like to do is also teach it maybe to like kind of like have a conversation, so it kind of can take turns in answering questions that we give it, right? That's what we get out of ChatGPT. So the question of so the issue is basically, how do we modify this beast that comes out of pre-training so that we can get useful, and then, well, as we'll see later on, there's other things to consider in terms of alignment. But we want to go through alignment. So let's talk a little bit about the current alignment practice. Okay, so the very first step of alignment is supervised fine-tuning, SFT. And you're going to be doing this in recitation. But one of the primary things this does is it makes so you can capture instruction following behavior. So I can ask a question and get an answer. Okay, that kind of thing. The second step is usually based on reinforcement learning, although this is kind of changing. This is kind of a lot of research going on here. We're going to look at the kind of the classic reinforcement learning method in the next lecture. And that basically is RLHF, so reinforcement learning from human feedback. And what we want then is we want it to give helpful responses, so responses that tend to seem like they're more, kind of following what was asked for, and then also safe responses. So that this tend to be the two dimensions that people look at. So helpful, if somebody asks it, how do I make a bomb? You can get a helpful answer, which would be telling you how to do it, but that's not safe, because we want to kind of rule that out. Or like just like it kind of like, there's a lot of like stuff you don't want it to be repeating that it picked up off the internet. So we want to kind of stamp that out. We want to kind of put smiley faces over Shoggoth in those areas. The third step, which we're going to be talking about in the next lecture, is going to be reasoning. So that's this kind of reinforcement learning through verifiable rewards. So this is important for kind of computer science and logic problems, programming tasks, that kind of stuff. But let's just look at SFT. It's very closely related to the supervised learning, transfer learning. So okay. Well, here's what we do. Here's the overall kind of steps that we take. So we assemble or buy a large corpus of prompt, completion, or instruction response pairs. Okay, so these are examples of somebody asking a question and then getting an answer, getting an answer out. So we have all those, and then we use a special token. And inside the recitation, we're going to use a special token, a pound sign, to represent the instruction, then pound sign, response, and then dollar sign. Enough. That's it. That's all you need to answer. Okay. So these special tokens play really critical roles. And this is from the Llama paper. They were stressing that quality of the corpus is more important than quantity. Okay. So then what we're going to do is we're going to cram down this corpus down using basically supervised learning. Basically, is what we're going to do. We're going to cram this down over the Shoggoth, over the pre-trained model, and that's going to yield us T instruct. So it's the exact same predict next token as used in pre-training, but it's like what we're doing is we're rewarding those tokens to do this. Okay. So what does the pound sign represent? It represents a call to chat. To what extent does it? It does. What role does the end response play? Well, it's to kind of close things off. Right. Okay. So for Llama 2, tens of thousands of curated instruction response pairs were used in SFT. Okay. Probably a lot more now. And yeah. So so I think now what we'll do is we're just going to kind of nose into some code here, and we're going to see this working over the little animal example from recitation. So let's go into the code to see it.
There's no model PT. Okay. So what we're going to do is we're going to have a big turtle. Let's start out with the big turtle. And then from recitation, you guys already saw this. We have the stories, which is basically this, like a poor rabbit admires an old frog, etc., etc. And let's see, what are we going to say here? Okay, the turtle loves the cat. The turtle loves the cat. Let's keep an eye on turtles and cats. Okay, let's keep an eye on the turtles and cats because we want to see what we can get with that. All right, now these are the SFTs, semantic fine-tuning corpus here. Right. Okay, so you guys can see this, I'm assuming? So what do we have here? We have a whole bunch of instruction following behavior. So I say, who does the young rabbit bites? Okay, that's a little bit funny. A rabbit. Who does the young dog bites? A poor cat. Okay, so these are a whole bunch of questions of like, now we have these special symbols now that we had before in our vocabulary, but we were never using. This pound and this kind of end of sentence, this or end of response. So this is the end of the question is represented by a pound, and the end of the answer is represented by a dollar sign, right? Okay. So what we want to see here is this, and this is something to keep in mind here. So we look at the stories here. A turtle loves a cat. So let's take a look at what we're training on here. A turtle loves a cat. So let me just do a search. Turtle. Okay, there is no turtle in the training set. So this is, and I don't know if there's a cat. There is a cat in the training set, but there's no turtle. So the turtle is absolutely, now the turtle is in the pre-train, because here it is, the turtle loves the cat, and the turtle happens to love the cat. And why does the turtle love the cat? The turtle loves the cat because the cat is aggressive against the rabbit, and the turtle and the rabbit are racing. That's the reason why, if you want to know. So let's go back here and let's train up Big Turtle. So here's what we're going to do. We're going to train Big Turtle, and then we're going to do that by basically saying, pre-training here. So it's just going to go over the stories here. It's going to build a representation, including the turtle loving the cat. That's going to all be in there in the pre-trained model. And then what we're going to do is then we're going to switch over to SFT, which takes these right here and crams these down on top of the model. So it's going to actually go in and it's going to change the parameters of the pre-trained model to reflect these. Okay. And then what we're going to do after that is we're going to put in questions like, who does the turtle love? And what should the answer be? The answer should be the cat. Who does the dog bite? God only knows what's going on in the distribution earlier. But it should give us an answer, the actual answer. So what this is doing is this is training this instruction following type of behavior. Does that make sense to people? That's what we're, so let's just get this going. Right. And also you guys will get to see roughly how fast it works on this Lenovo I have with this kind of Blackwell, the GPU. Okay, so anyways, we have no model. Let's start her out with a pre-training and let's run it. Not debug it, let's run it. Okay, boing. Okay, so here we go. And it's 2.29 million parameters and things. Okay, all right, and as model, the model.pt. So yeah, the loss got down pretty well. I think I was running it for like what, 5 or 6 minutes until I decided that it was interfering with the video. And yeah, so we're getting here. We're getting pretty good results. The frog, okay, the frog hates the clean rabbit. The rabbit hits the poor cat, etc., etc. Okay, so yeah, so it's got that. Let's see. All right, so I hope I didn't ruin it, but okay, there we are. Now let's do this. Let's go and let's do the yeah, let's do, and I'll pause this very quickly. So I'm gonna put this on SFT here. Okay. So the way SFT is going to work is what we're going to do is we're going to well, we load in the model here. And I think maybe if we just run it, we'll see how it's working. Okay. I just want to make sure I have when it does that, trainer. So I go to the trainer and I just want to put a pause in here somewhere so that, all right, while true here. Okay. I think we can do it this way. I'll just put it there for now. Okay, so what do we have? I go back to main here, and what we want to do is we want to do SFT. So we want to do here. Okay, so the usage we're having here then is going to be SFT because that's what this gets that element. Right, let's just run it. Let's just debug it so we can break it. Okay. I'll show that later. Okay, so here's the prompt we put in now. Who who does the old frog hate? A poor rabbit. But then there's all this junk here. See all that right there? Let's take another look at one. Okay, that's one iteration. So this has a separate loss because it's doing the loss over the SFT corpus. So it's doing the loss over these guys right here. So it's saying, yeah. So let's see here. Okay, who does the old frog hate? Then that's the question. And then it just like a whole bunch of junk here. Okay, so it's not doing very well at all. So now let's just let it rip here. So we're gonna let it rip, let the loss come down. Okay, now what are we gonna get here? Oh, look right there already. Who does the turtle love? The cat. So it's already kind of it's okay. Who does the okay? And by the way, when it reaches the dollar sign, the reason why you don't see the dollar sign because that signals the end of the completion. So now I'm asking it, who does the dog bites? A frog. Okay. And if I'll just let it rip here. But do we see what's going on here? What's happening here is that we're trying to predict. What we're doing is we're basically saying that we're trying to predict. How am I going to say this? These are the SFT are these are the input output patterns. So what it's doing is it's burning these into the network, so that who does a cat nose with a pound sign, a clean cat. This is going and then dollar sign here. So it's going in, it's modifying the weights of our GPT to produce these to memorize this set here. So it's cramming that down on top of the pre-trained weights. And if we look here, we are getting it. We're getting really good kind of instruction following behavior. So look at this. Who does the turtle love? The cat. So it's giving us the right answer. So what it's been able to do then, this is kind of the key point behind this. Notice here that it was learning all this instruction following behavior just by, what is it, 100 examples? No, 1,000 examples. Or 500 examples. 1,000 examples. It has 1,000 examples, but none of these examples are even mentioning the turtle. The turtle is nowhere to be found in this training set. But because the turtle was found in the actual one sec, the actual background knowledge, the turtle loving the cat was represented here in the background data. But then once we trained it, look what happened. We trained it over this instruction following behavior that never even mentioned a turtle. And then when we start querying the thing and we ask, who does the turtle love? The cat. So it's short. This is showing it the transfer learning of the background knowledge with the SFT and getting this instruction following behavior. So I hope that's clear to people that it's an impressive thing that it's doing in terms of just being able to now follow instructions just by this simple SFT, including SFT in the process. So that is something that you'll work with on recitation number 2 to get your own kind of sense of this. So I hope that's clear.